Good evening, everyone. So, in this video, today in the video lecture, we'll be discussing about the concepts behind the structural analysis using the matrix methods. So, these are the very powerful methods which by which we can actually solve all the types of structures, either the beam members, truss, and also the frames, both in two-dimensional and also the space truss and space frames also using these members. So I will be discussing about how we generate or how we generate the stiffness matrix initially, and then we can solve one beam and one frame kind of a problem using the stiffness matrix method. So in this, again, I'll not be discussing about the flexibility method, because the flexibility method we have already been using it in the previous video lectures. So if you remember, we are using the flexibility method to by using the compatibility conditions, and then we are trying to uh, we are trying to generate different types of equilibrium equations along with the compatibility conditions, and that is how we have actually used the flexibility method. So uh, basically, it is again using the combined. This is again the same. Actually, in the flexibility method, what we usually do is we usually apply unit load, and we'll find out what are the displacements at each at different joints, or at different connections, or at different joints or at different nodes. Whereas in stiffness matrix, we usually give a unit displacement. Again, the displacements can either be the linear displacements; those are the vertical, horizontal, or whatever it is, and also the rotations. Okay, so we'll be giving unit displacements at the known nodes, or at the joints, or at the places where we actually wanted to find different types of different types of forces, like the bending moment, or the shear force, or axial force. And then we'll find out what are the end forces in the members by and then we usually develop the stiffness matrix from it. So anyways, again, having said that, we'll try to go from the basics to understand to generate the stiffness matrix. uh, uh, so initially we'll just start with generating stiffness matrix. So the first and foremost condition to start to derive stiffness matrix is actually, let us say, again, if you remember, if you actually understood what I was telling just a few moments ago. I was saying that um, for the stiffness method, or for the stiffness matrix method, what we usually do is we actually uh, initially we'll be giving a unit displacement. I mean, unit vertical displacement or horizontal displacement, and also the rotation, and we'll try to understand what is happening and what are the forces generated because of it. Okay, so in linear terms, I think it is very easy for us to actually imagine, or kind of understand what is stiffness. So stiffness is nothing but let us say stiffness K is nothing but load per unit displacement. This is what usually usual definition of what the stiffness which we have been learning so far. So again, let us assume a spring. Okay, so we'll assume a spring, and the stiffness is nothing but, if you're giving a displacement delta, what is actually force which is developed inside the spring. So that is what the stiffness is, right? The K is nothing but you see what we usually, so for each, so you keep on increasing the delta, that is, let us say you start with 1 mm, 2 mm, 3 mm, and so on. And then what you'll do is, let us say this is P and this is delta. So you will measure the force which is coming at this joint, which is the fixed joint. You'll try to measure the force at that joint, and you'll keep on increasing delta. So let us say initially this end is at this position, okay, and then you keep on pulling it, okay, you keep on pulling this, you keep on pulling this end for each increment, okay, you keep on pulling this for each increment. So let us say this is 1 mm, 1 okay. So what I'll do is this is 1 mm, then this is 2 mm, this is 3 mm, so on and so forth. So 5 mm, and then you'll also measure what is the force for each displacement step. So if you plot that, let us say for 1 mm, 1 2 3 4 5, okay. Let us say for 1 mm you have something like this, for 2 mm something like this, 3 mm your force is here, and so on and so forth. So you just drop a line like this, okay, and then you find out the slope of this line. Slope of this line, slope is nothing but k of this line, okay. So how much the force is generated in the spring if you are pulling it by one unit, so that is called the stiffness. Similarly, this is actually easy to understand, but when we are having different types of members, so what are the different types of members which we came across in structural analysis? So we have truss members, okay. So truss members are like, simple line members, and we I'll just write it as truss members, fine. Next one, I have a beam member. I'm just right now I'm just drawing a line diagram, uh, but what is actually what's the difference between each member, I'll be just explaining in a moment. So this is beam member, and this is a frame member, okay. So these are the different types of members which we usually come across, which we came across and we have analyzed so far. So now, what differentiates between each? So for a truss member, let us say this is one node and this is another node, okay, or this is one joint and another joint. So at the joint, we can have 2 degrees of freedom, right? It can either go in this direction and in this direction. So it can have 2 degrees of freedom, okay. And we assume that the truss members are axial members, right? Axial members, and uh, there's no moment in it. Why? Because the joints, again, if you remember our initial video lectures, in that we were discussing about the assumptions of a truss member. So the joints are again assumed as a pin members, and the self weight, we are ignoring the self weight, or we assume that all the loads which are acting on the truss are actually acting at the joints, okay. It's not at it is not acting within the joint, within the member, it's acting at the joints. So because of that, it can have 2 degrees of freedom at each joint, 1 2 3 4, okay. So again, that is again by definition of the truss member. And what about the beam? So for the beam, again, when we discussed about the beam members, again, there are the beam members. Usually we assume that it is carrying a gravity loads, right? Gravity loads, what are the gravity load means? Gravity load means only the vertical loads. So you can have 1 degree of freedom like this, 1 degree of freedom like this, okay. And in addition to this, we can also have a joint rotation, okay. So let us say 1 2 3 4, we have 1 2 3 4, okay. So again, 2 degrees of freedom at each joint, 2 degrees of freedom at each joint. What about the frame member? Frame member is again frame member is like, you can It can also have, in addition to the beam member, it can also have an axial uh, compression or axial displacements. So it can have something like this. So let us write it as 1, 2, 3, 1, 3 and 4, 5 and 6. Okay. So I have 3 degrees of freedom per each joint. Okay. So again, we are. I want to use the same notations which we are using previously. So this is what my notations are: right side positive and upwards positive, and my clockwise. Sorry, it is anti-clockwise rotation or anti-clockwise movement. I take it as positive in this. Okay. So we need to stick on this so that we'll not get confused in while we are deriving all these things. So again, coming back to the stiffness and definition of stiffness. What the stiffness is, we already learned that the stiffness is nothing but the load per unit. Uh, if you are actually giving a unit displacement, what is the load it is going to carry? That's what stiffness, right? Again, for the linear members or for the string, let us say for the spring, uh, it can only go in axial direction, right? You can either, again, spring can be either pulled or you can either compress it. So what about the beam? Okay, if you have a beam, then what are you going to do with the beam? So for the beam, it can be you can have a shear coming there, and also you can have a rotation happening in the beam, right? You can also have a rotation happening in the beam. So now let us move on and let us generate so stiffness matrix for a beam members. Okay. So first and foremost, first we need to understand what are the degrees of freedom which we have for each member, and once we obtain the degrees or once we derive or once we know the degrees of freedom, then we can generate the stiffness matrix. So again, why do we need to generate the stiffness matrix? So I'll try to explain it now, but maybe once we derive it and then we will get, then I think that will be more clear. So right now what we are defining k is nothing but p by delta. This is again in the linear terms. So force is nothing but k times delta. Okay. So again, the main goal or the main aim of this analysis is to understand or to find out the end forces or the support reactions or the internal forces, right? So once we obtain the internal forces, from there on we try to build on and we try to design the beam, design the members to resist the loads which we already analyzed for, right? So we actually wanted to find what is p. Okay. So these are we wanted to know what is p. So that means we wanted to find out what are the forces. So let us say, again, this is for linear or one dimension, which is like spring. For a spring, example spring. Okay. But the same can be actually applied for a beam member or a frame member or a truss member also. So the same thing can be applied, and we can say that F is equal to K times D. So the forces which are generated in the members can be is equal to stiffness of the member times the displacement of the member. All right. So once we know what is the stiffness matrix, and if we happen to know what are the displacements uh, in the member, okay, so then we can directly find out what is the force. So k is actually stiffness is always, it is kind of a it is not a it is directly not a constant, but if we actually assume, for example, we have different types of beams, right? If we have a cantilever beam, we have a simply supported beam, uh, we have a continuous beam, we have a prop cantilever, uh, we have many types of beams or many types of many types of support conditions, right? But if we can actually generalize that thing, generalize each generalize each condition, and if we try to derive an equation, or if we try to make a generic stiffness coming out of each matrix, each problem, then we can actually apply the same thing to all the systems. Okay, to all the systems, and then we can actually derive the forces. We can derive the reaction forces. In turn, we can actually find out the internal forces, and then at the end we can draw shear force diagram, bending moment diagram, etc. So again, for this, what we usually do is, for the stiffness, in order to generate a stiffness matrix, we always assume the beam is a fixed beam. Okay. If you remember, we are doing the same thing when we are actually developing a moment displacement, slope deflection equations, right? So we are actually assuming a fixed condition, and then we are actually rotating it and doing it. There we are actually trying to uh, initially find the moments, fixed end moments, and then if there is a release, we are releasing it, right? So similarly, we will be doing something like that in order to generate the stiffness matrix also. Okay. So one more thing. Again, this is not a straightforward thing here. So this is, if it is f, the forces, let us say the reactions, or or the applied forces, or whatever it is. So the forces at the joints, or at each degrees of freedom, is equal to stiffness multiplied by d. Okay. So this is the matrix. So now the matrix terminology comes into the picture. So uh, what I mean by matrix is that, so let us say I'll take a beam. Okay. So this is a beam. So how many degrees of freedom uh, does a beam member have? So the beam member, actually, this is 2 degrees of freedom per node. This is per node. This is per node. Okay. So the beam member actually has 4 degrees of freedom. One shear, or the vertical, and rotation. Okay. So what I'll do is, this is 1, this is 2, 3, 4. I want to just label each degree of freedom there. So 1, 2, 3, 4. So this is, I'll call it as A. This is B. Okay. If this is a beam member, I have 4 degrees of freedom. 1, 2 are actually the degrees of freedom at the joint A. 3 and 4 are the degrees of freedom at the joint B. So now each degree, like we have 4 degrees of freedom here. Then what is F actually corresponds to this? Okay, the force vector, or the force. See, the reason why I'm calling it as a vector is, vector usually is a column matrix, right? It is a n by one matrix, n by one kind of a matrix. So the force. So for each, let us say, if I am displacing if I'm having a displacement at each node, okay, at, at a particular degrees of freedom, what is it actually generating there? What is the force it is getting? It is generated there. Okay. Sorry. Yeah. What is the force it is actually generating because of that? So that is what my the force replies. So I'll just write it down now, that F1, F2, F3, F4 is nothing but the stiffness K times D1, D2, D3, D4. Okay. So now what is F1? Okay, what is F1? F1 is nothing but the shear force here. This one. Okay. So F1, let me write it as, this corresponds to F1, and F2 is nothing but the movement here. F3 is the shear force at the joint B. F4 is the moment at the joint B. Now, what is D1, D2, D3, D4? D1 is, again, what is my displacement in one direction, direction 1. Okay. So this is vertical displacement. Vertical displacement at A. D2 is rotation of rotation at A. D3 is again vertical displacement at B. And when it comes to D4, D4 is again rotation at B. Okay. So again, if you just know what is K, what is happening, what is the stiffness matrix, uh, you can actually find out uh, either forces or either unknown forces or unknown displacements, whatever it is unknown. Okay, fine. Let us just go ahead and derive the stiffness matrix. So let me have a beam. We have a beam. Okay, beam member, and we have already marked what are the degrees of freedom, right? This is, I just mark it as, this is 1. Okay, this is 1, 2, 3 degrees of freedom, 1, 2, 3, 4. Fine. Now by the definition of the stiffness matrix, okay, let me first uh, again, what is the stiffness? Stiffness is per, what is the force in the member due to the unit displacement, right? So now we have 4 different types of displacements which are possible in this member. One is along A, direction A. One is along B, that is direction 2. Sorry, the second one is along direction 2. So along direction 2 is nothing but it is a rotation, unit rotation. Along 3, again it is again a vertical displacement upwards, and 4 is nothing but again a unit rotation clockwise at B. Okay, so now let us say, let unit displacement, okay, this is A and B, unit displacement is applied at joint A. Okay, now one more thing which we need to understand is, again we are actually discussing about the fixed conditions, right? So we are actually uh, uh, considering it as a fixed condition, and then we are actually going to develop what are the forces generated due to these unit displacements. So what happens if you apply a unit displacement at that location? So what happens is that now now this is my unit displacement. Okay, so this is how my beam is going to bend. Okay, so I mark this as unit delta equal to 1. So now you see it is in the direction of 1, right? So when you are actually giving a unit displacement, you need to actually you fixity in all the other degrees of freedom. Okay, so it is again just it is like a support settlement. Okay, so you have given delta equal to 1, and because of this delta equal to 1, you need to find out forces in the directions of the degrees of freedom. So you need to find the shear force at A, you need to find moment at A, you need to find moment at A and the shear force at B. Okay, so now I think again last time we were discussing the same thing. So we have this, and if we, the support is settled by, let us say, delta equal to 1. If you remember, it is 6 EI delta by L square, and the moment here is also 6 EI delta by L square, and the support reactions are 12 EI delta by L cube. This is 12 EI delta by L cube. I hope you remember this kind of formulations. Otherwise, you can again you can simply do this conjugate beam method, and then uh, you can find out these formulations. So Again, I don't want to repeat the same thing. So now what happens here is that now because of this, you have a force coming like this and force coming like this is 6 EI. So delta is 1. Okay, I'm not writing delta. 6 EI delta by L square, and this is again 6 EI delta by, this is 6 EI by L square. You have this motion, so it should be downwards here. So 6 EI plus 6 EI by L, so that is 12. 12 EI by L cube. It has to balance, so this is 12 EI by L cube. Okay. Now, okay, we found out what are the support reactions. Now, how to find out the forces? Okay. Now, because of delta equal to 1, okay, so delta equal to 1, we have force. Again, I'm just writing, I'm just drawing the same thing. Now I'll be labeling the forces. Okay, because delta equal to 1, sorry, because delta equal to 1, F, okay, the force at 1, okay, force in the direction 1 because of delta at 1. Okay, this is F, that is why we usually call it as F11. Now, force in the direction of 2, that is nothing but the moment because of the unit displacement in the direction 1. Okay, this is F21. Similarly, we have F, sorry, this is F41 because the moment degree of freedom is 4, and we have F F31. Okay, now I think now you can relate to this. So F11 is nothing but minus 12 EI by L cube. Is it minus or is it? Yeah. And what about F12? F12 is going to be plus EI. Okay, plus EI by, okay, this is in this direction and this is like this 12, so this will be positive and this will be downwards. This is plus EI by L cube, and F21 is how much is F21? Is it positive again? 6 EI by L square. F F31 is downwards, so downwards it's negative. 2I by L cube. F41 is, this is positive. Okay, so this is what we have obtained. This is the final equation which we have obtained. Now what about the other one? Now now this is when the delta equal to 1, and that too the delta is in 1, the what do you call it? It is in the direction of degree of freedom 1. Okay, now if you want to obtain the next terms of the stiffness matrix, so what you'll do is you should have a fixed condition again. And what is my second degree of freedom? Second degree of freedom is a rotation. So what I'll try to do is I'll try to rotate. Okay, I'll try to rotate in this theta equal to 1 unit. So if theta is equal to 1, if you remember what we are so what are the solution for that? So theta is equal to 1. So this is, so again this is something like this. Theta equal to 1, so it will generate, you need to have a 4ei theta by L moment over here, and this will have a uh, half, right? You have a carryover factor. So 2ei by L coming here, and this is complete. This is actually rotating this end in anti-clockwise direction. So you should have a clockwise force, or the moment that has to be clockwise, so that to resist to this force. So this is downwards. That is going to be, sorry. That is going to be 2 plus 4 is 6 ei by L square, and this will be upwards 6 ei by L square. Okay, so the same thing which I'll be writing it down now. So now F in the direction 1, because of the load, the unit load in the direction of second degree of freedom. So that is going to be 6 ei by L square. F 2 2, that is force in the member in the second degree of freedom due to the unit displacement in the second degree of freedom. That is going to be 4 ei by L. Next, F 3 2 is going to be, what is 3 2? Minus 6 ei by L square. F 3 4 is going to be 2 ei by L. Okay, similarly you can find out what is F13, F23, F33, F34, F43. So F13, again F13 is the force in the first degree of freedom, in the direction of first degree of freedom, because of the unit displacement in the third degree of freedom. Okay, so again when you're giving a unit displacement, you will be fixing all the other degrees of freedom, so that has to be kept in mind. Okay, yeah, so this is going to be, so this, if you work out, this will be F minus 12 ei by L cube, minus 6 ei by L square. This is 12 ei by L cube. This is minus 6 ei by L square. Similarly, 1 4, 2 4, 3 4, 4 4. So this will be 6 ei by L square, 2 ei by L, minus 6 ei by L square, 4 ei by L. Okay, fine. So let me write everything. Fine. Just let me understand what actually I have done here. Okay, so initially I was for each degree of freedom, I'm trying to displace it in by unity, and then I'm trying to find out the forces in it, right? So what am I doing? What I'm trying to do is, when I'm doing that, I'm trying to make the other degrees of freedom as zeros, right? So now the forces are nothing but, again we said it is k into d. Okay, this is again the matrix multiplication. So F, now again coming to the size of the matrix, it depends on the degrees of freedom. So it depends on the kinematic determinacy, kinematic indeterminacy. So for a beam member, what is the kinematic indeterminacy? So far what are we have seen it, what is the kinematic indeterminacy? We have 2 degrees of freedom for each node, right? 1 2 3 4. So dk is going to be 4. Okay, So um, the stiffness matrix is 4 by 4. That is again that is straightforward. It is the stiffness matrix. The size of the stiffness matrix will be 4 by 4. It is the size of the stiffness matrix is actually the number of degrees of freedom. That will be the size of the matrix. So let me write down now. So this is 4 by 4. Okay. How many displacements do we have? So displacements is nothing but the degrees of freedoms, right? So those are four degrees of freedom we have. How many forces are possible? Forces are nothing but if you restrict or if you restrain the displacement, that restraints is nothing but the force, right? So you have 4 degrees of freedom. So four forces can be generated if you are restraining them. So now let me write down F1, F2, F3, F4 is nothing but uh, let me write down this as, okay, I'll just write down it as K11, K12, K13, K14, K21, K22, K23, K24, K31, 32, 33, 34, 41, 42, 43, and 44. Fine. So the displacements, as we have seen, we have 4 degrees of freedom, so 4 displacements are possible there. Okay. Fine. Now just we'll go back and see what we have done earlier. So what we have done earlier is we try to find out the forces in the first degree of freedom. Okay. We try to find out the forces in first degree of freedom, and and we have restrained the other degrees of freedom, right? And we have restrained the other degrees of freedom. So that means we have given a unit displacement in the first degree of freedom. That's what I meant. So in that case, what happens? So D2 will be 0, D3 will be 0, and D4 will be 0, right? So now we already calculated what are the forces. So F11 is nothing but actually F1, right? So F11 we already know how much is that. 12 EI by L cube, 6 EI by L square minus 12 EI by L cube, 6 EI by L square. 12 EI by L cube, 6 EI by L square minus 12 EI by L cube, 6 EI by L square. Fine. I'm just going to write down this as, I'll just write it down as K. I don't want to write everything now. So this is 1 0 0 0. Okay. Now what does this mean? So K11 is going to be 12 EI by L square. Fine. Okay. And what about K22? K12 is going to be 0. Okay. K K K K31. Sorry. All these things are going to be now K11 times 1 plus K12 times 0 plus K13 times 0 plus K14 times 0. Okay. Now this is K22, K21, K22, K31, K41 plus zeros plus 0 plus 0. Fine. Now you need to understand. So K1 is nothing but F11, K2 is nothing but K21, K31, and K41, and so on and so forth. Okay. So if we just write down in terms of a matrix, now the K matrix, stiffness matrix, can be written as K11 is nothing but 12 EI by L cube, 6 EI by L square minus 12 EI by L cube and 6 EI by L square. Okay, that is what we have obtained it. So 12 EI by L cube, 6 EI by L square minus 12 EI by L cube, 6 EI by L square. Okay. and K21, K22, K23 we have already found out here, right? So K21, yeah, where is K21? K21, yeah. So we sorry, we have K12, right? K12, see K21 we have already have. We have used it here. So we have K12, K22, K32, K34. So those are nothing but these values. These values K12, K22, K32, and 6 EI by L square, 4 EI by L minus 6 EI by L square, so on and so on. So that is 6 EI by L square, 4 EI by L minus 6 EI by L square, 2 EI by L. Similarly, we will get this thing 12 minus 12 CI by L cube minus 6 EI by L square, 12 EI by L cube minus 6 EI by L square, 6 EI by L square, 2 EI by L minus 6 EI by L square, 4 EI by L. Okay, this is the stiffness matrix for the beams. Okay, so for a beam, this is my stiffness matrix. So if you know this, you can find out for different. So what I'm trying to say is F1, F3, F4. This times D1, D2, D3, D4. 4 by 1, this is 4 by 4, this is 4 by 1 matrix. Fine. So in case if there is some support rotations and support settlements, okay, in case if you have, let us say you have uh, you have support rotations at let us say you have support settlement or support rotation at A, joint A. What is this? Is my A, this is my B. Okay, let me assume both are uh, fixed supports. Okay, both are fixed supports, and we have 6 EI. This is EI, and the length is L. Okay, so let us say at joint A there is a support settlement of 1 unit. Okay, the support settles by 1 unit, and also there is a joint rotation of 1 unit in the clockwise direction. So this is something like this. Okay, so in that case, what is actually given in the question? That it is given that D is equal to 1 unit, and even D2 is also 1 unit. Okay, so you have both support settlement and rotation. So what are the forces generated because of that? That can be found out by this direct matrix multiplication, right? Uh, you want to find out what are F1, F2, F3, F4. You know what is D1, D2. Do you know what is D3 and D4? Absolutely yes, because D3 is 0. There is no downward displacement at joint B, and there is no rotation at joint B. That means D3 is 0 and D4 is 0. Just plug in these values, you can directly find what is F1, F2, F3, F4. This is a very simple condition, but uh, if you want to find out anything which is if you want to find out any different types of joint rotations or joint displacements um, or any of that things for such matter, we can directly find you can use this stiffness matrix, and then you can directly find out what is happening there. So again, this is again introduction, so that is the reason why I'm only explaining how the stiffness matrix is generated. If you go for a higher level or higher if you go for a um, if you go for an advanced course on structural analysis, So that is nothing but advanced structural mechanics, something like that. So in that you will actually find how to analyze uh, how to analyze the members, which are like how to analyze members, and if you have an inclined members, so how to make use of transformations. Because in this, again, in this, the main important thing is we actually assumed our Cartesian our coordinate system, something like this, right? So this is 1, this is 2, and this is 3. So what if you have a beam like this, something like this? So in this is 1, this is 2, this is 3. So if you want to find out shear, then I think it should be along the beam, right? So the shear force is something like this, and the axial load is something like this, and the moments, again, moments doesn't have any problem. But if you want to find out the shear force and bending moment, you need to actually rotate your axis, and then you need to find some transformations, right? So those transformations I'm not covering, and will not discuss in this, because that anyways we can, once we start learning about the advanced methods of structural analysis, we can actually study in that, in that during that courses, or in that courses. So so far, again, if you can observe, what we have done is we have done only the joints. We are just playing with the joints. We are rotating it, we are displacing it, we are rotating the other one, we are fixing the other degrees of freedom. What if you have an external load? So usually the beams always carry an external load, right? If not the external load, it will carry its own self weight, but we can't simply neglect the self weight, because the sibling structures have a huge self weight which is carrying, right? Almost 50% of the load actually coming to the structures are because of the self weight or the dead loads, right? So we can't simply ignore the loads coming. Okay. So what happens in that case is, let us say, so far we are again discussing, again I'll just I keep coming back to this point all the time. So so far what we are trying to do is, let us say if I have a member something like this. Okay, I have a simply supported beam. Let me say this is a simply supported beam. Okay, simply supported beam. Okay, and we have a UDL. I know this is a very easy example, but please bear with me. This is UDL is W kilonewton per meter, and I'm also applying a external load, M external, or I'll just call it as M. Okay, I'm applying an external moment at joint B, roller support B. Now, what did we assume during the stiffness matrix? We have assumed that the beam, whatever it is a fixed condition. Okay. So what we can actually do this is, we can try to say that this can be the fixed beam. Okay. Uh, with with the given loads. So given loads are, let us say, some random load. What I mean, the same thing. It is again the same load. W kilonewton per meter. Okay. For the fixed beam, you are applying M. Okay. Plus, now we are assuming those joint rotations and joint displacements and all stuff, right? So those will be, sorry. And we have all these joint rotations, and I'll also cover. Okay, I'm just showing something a little fancier, because I just want to show rotations happening in. Okay, there is both the rotations and displacements happening. Let us assume that there is something rotation and displacement happening. Okay, so yeah, so how do you find this? Again, for this we already have we have already derived, right? If you remember, we have derived this. F is nothing but K times matrix multiplication of stiffness matrix. Okay, so these things are actually related to this, and we also have this. So if we how do you find the moments. Huh? So the moments are nothing but you have this. Because of this, you can you will also obtain what do you obtain? You also obtain uh, fixed end moments, right? We are calling it as fixed end moments. So you have fixed end moments. Now we have forces due to fixed end moments plus what is the forces because of my joint rotations and joint displacements? It is k times d. Okay, that should be equal to my external loads or the externally applied loads. That is nothing but m. So far I have only let us say I have applied only a moment at that joint, so I'll be fine. I'll be doing this kind of things and uh, see, in this I have applied only moment at this joint B, right? So I'm just writing it as m external. But what I'll do in this case is in the other direction of in other directions or other degrees of freedom, the forces are zero. That's what I mean. Okay. So this is how we account for the loading coming onto the members. Okay. So again, just a quick recap. So what we try to do is, if we have an external forces coming, okay, if we have an external forces like an external UDL, we'll try to find out the fixed end moments, and the fixed end moments are one type of a reaction forces, right? And what are the other what is the other one which can be possible? The possibility is that is nothing but the stiffness matrix times the matrix multiplication of stiffness matrix and the displacement vector. So if you multiply both, what we'll be getting? We'll be getting the forces, the forces actually at the degrees of freedom. So if you add both, that has to be equal to the applied external loads. Okay. So if you add both, that has to be equal to the only then the equilibrium will be satisfied. Okay. So in flexibility method again, in flexibility method we are actually trying to uh, make use of compatibility conditions. Okay, we'll find out the displacements. We will try to find out the 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 displacements due to the unit loads, and then we'll try to apply the compatibility conditions there. But in this, what we are trying to do is we are trying to find out the forces, and then we'll check for the compatibility. So that is where we are going to draw uh, the results for the redundant forces or the results for the unknown forces. Okay. So we'll take up one question, one simple question. So one simple question again. We'll take up a question on the fixed beam. Okay, this we already know about the solution for this, but for the sake of solving using the stiffness matrix method, I'll just show this. I'll just try to solve this question again. So the question is something simple. So you have a okay, you have a fixed beam, and over which you have a loading profile of W kilonewton per meter. Okay, and is that the question? Okay, W is nothing. W is given as 10 kilonewton per meter. Length of the beam is 12 meters, and E is equal to 200. So it's a steel section. I is given as 300 times 10 to the power 6 mm power 4. Okay, and there is one more condition which is given here. So the condition is uh, A and B. Support B settles by 5 mm. Okay, this is question A, and B part is settles by 5 mm. Only support B. Okay, again only support A rotates by 1.5 degrees. Okay. Now, what are the forces? What are the bending moment? What are the shear force generated because of this? Uh, so you have external load coming, and also you have a support settlement at B, and also you have a support rotation at A. Both are again not the same. It is again happening not simultaneously. Anyways, if it is happening simultaneously, we can do okay. Maybe C uh, simultaneously. Simultaneously A comma B. Okay, fine. How do we solve it? Is again easy. First, we find out fixed end moments. You have to be very careful when you are writing the fixed end moments because what is our sign convention? Upwards positive and clock anti-clockwise positive. Okay, so fixed end moments are fixed end moments. Now I need to write it in terms of a matrix. 1, 2, 3, 4, 3, 4. Okay. Oh, sorry. Sorry. Okay. Now, what is external moment M1? M1 is WL by 2. Okay, first let us calculate that also. WL by 2, 10 by 12 by 2, 60. 60 positive. And what is the other one? WL square by 12. That is 10, 12, 12 by 2. 120. 120, 60 minus 120. Okay, because you might be knowing why. Okay, that is the reason. This is my fixed end moment. So this is my M external. Okay, M external. This is I read it as M external. Okay, fine. Now FFEM is nothing but M external minus K times D. Okay, so F fixed end moments or the support. Let me call it as support reactions again because we get confused here. This is support reactions is nothing but M external minus K times D. Okay. K again. So beam member we already derived what is the stiffness matrix for the beam. So M external is going to be 60, 120, 60 and minus 120. 60, 120, 60 and minus 120. So stiffness matrix again. I want to write the entire stiffness matrix here. I'll just check whether if I can copy paste it. Alright, anyways, this is what my stiffness matrix looks like 12 EI by L cube, and let me write down again just for the sake of completion. So this is 12 EI by L cube. I hope you might have observed here. You can see okay. So you might have seen here, right? It is symmetric. The stiffness matrix is symmetric. So why is it symmetric? Because you already know, because the, the F12 is actually equal to F21, because it is actually the same scenario, right? You are actually trying to restrain the other degrees of freedom, and you're doing the same thing at the other end. Okay. Anyways, I'll just write 12 by L cube 6 EI by L square minus 12 EI by L cube 6 EI by L square. This is 4 EI by L minus 6 EI by L square 2 EI L 12 EI by L cube minus 6 EI by L square, and this is 4 EI by L. This part is symmetric. This is similar to this. Okay. 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 I didn't have space to write D. Okay. D is again D1, D2, D3, D4. Now, now again, the question is to find out what are the support reactions, right? So we have already computed what are the external forces. Okay, fine. What's the next one? The next one is K is already computed. Fine. EI and L square L cube values, also, everything we know about it. What about the D matrix? Okay, this is again the trickiest part. So the D matrix is, we need to find out what is happening at the D matrix, right? So do we have any information regarding displacement matrix? Yes, we have the information. So the information is, let us say we are trying to solve the first question first, which is 1A. In that, what is he saying? He's saying that the support B is going to settle by 5 mm. Okay, settle by 5 mm. Settle means it's going downwards, right? So that's what the settle. That's what we assume. It's not assumption. Settling means it is actually going downwards. So D1 is going to be 5. That's what I want to mean. But shall I take it as directly 5? We can't take it 5 because it is minus 5. The reason minus 5 is we need to be very careful about the sign convention. So in our sign conventions, the degrees of freedom upwards we are taking it as positive. So downwards it will be automatically negative. D2 will be 0, D3 will be 0, and D4 will be 0. Why? Because those are fixed. Okay, those are fixed conditions. So the rotation is 0 because in 1A, question 1A, the support is only settling by 5 mm. It's not rotating or it's not doing anything else. So you have 4 unknowns: F1, F2, F3, F4, and you have 4 equations to solve it. It is easy to solve, right? You can directly solve it. And what about B? Question B. In question B, the question is the support A rotates by 1.5 degrees. So here I want to emphasize on using of different types of units. Okay. Per se, the degrees again, the degrees are actually not the units, right? We actually develop everything in terms of radians. So even though if it is given as 1.5, if you take it as 1.5, then this is a huge rotation. You need to understand 1.5 radians is almost like half 1 pi by 2. What is pi? Pi is like 3.14 radians. Pi by 2 is almost 1.7, 1.65, something like that. Sorry, 1.55. Oh my, so 1.55 is like almost 90 degrees it has been rotated. So you need to be careful. So in that case, what you need to substitute is, so for case B, what happens is that D1 is going to be 0 because there is no settlement. Oh, I'm sorry. Actually, I made a mistake. So D1 is not going to be 5. Sorry. Okay, what is D1? D1 is at A, D2 is also at A, D3 is going to be 5, minus 5, and D4 is going to be 0, D2 is going to be 0, D1 is going to be 0. Okay, please correct this. D1 is 0, D2 is 0, D3 is going to be minus 5, and D4, because D3 is actually the degree of freedom at 5, at location B. and that is actually settling down, so that's why it's -5. Now in my question B, in B, what happens at B? In B, support A is rotating, right? What did I say? Support A is rotating 1.5 degrees clock and clockwise. Okay, anti-clockwise. So support B rotation anti-clockwise. D1 is 0, D3 is 0, D4 is 0, D2 is 1.5 times pi by 180. That's it. You just substitute this. You already know EI values, so you know stiffness matrix values. You can directly find F1, F2, F3, F4. Okay. So that is about the stiffness matrix for the beam members. Let us also try to generate the stiffness matrix for a for a frame member, and also let us see for a frame member again. There are some we'll try to solve something which is kind of an exceptional case, because in that we because I don't want to I don't want to touch on the transformation matrix and all. So we'll just solve one exceptional case for a frame member in which I am not considering any axial deformations. Okay, axial deformations I'm not considering. So if I'm not considering an axial deformations, what is my stiffness matrix going to look like? So that is one question. So I'll just solve that question, and uh, then we can stop for the session. So the question is something like this: we have a frame. Okay, this is a frame member. It is axially rigid. If I say if it is an axially rigid member, that means there's no compression. There's actually the member is not uh, deforming. It's not deforming axially. That's what it means, right? So if you are given a load P, which is acting something along this, okay. So you have a load P. There is a load. The load is actually horizontal. So actually acting like this. Okay. So this is EI and H by 2. The height is H by 2, and this is H, and this is EI. This is EI, and this is H. Fine. So axially, now what is given is members are axially rigid. Okay. So if the members are axially rigid, then there is no displacements coming from each member. There is no axial rigidity. So there is no axial shortening or elongation in the members. So find degrees of freedom, DOFs. How many degrees of freedom do we have? First question. B is derive stiffness matrix. Derive stiffness matrix. Okay. Now solving, how many degrees of freedom does this member have? Okay. Actually, it should have 3 degrees of freedom here. Come on. Okay, and 3 degrees of freedom here. So what are those three? 1, 2, 3. 1, 2, 3. Okay. All right. So three degrees of freedom here. Three. Now it is said that the members are axially rigid. Okay. So in the axial degrees of freedom, the member is not undergoing any deformations in that direction. Okay. So there is no settlement or there is no sorry, not settlement. There is no compression or there is no elongation happening in the members. That means I can actually remove three degrees of freedom from this. So I only have degrees of freedom are three. So I can remove the axial deformation in this, axial deformation in this, and axial deformation in this. Now what are left? The degrees of freedom that are left are when you push this member with load P. Now what happens is that okay, it can sway one delta, it can move rightwards, it can have a rotation that is theta, and it can have a rotation here that is theta 2. Fine. And there is no theta which is apart from this there's no degrees of freedom which is coming in this members. Why? The reason is that it is we are actually assuming it as a, we are actually told, or we are assuming it as a axially rigid member. So the axial deformations are zero in this case. So degrees of freedom is 3. That means what is the size of the matrix? Stiffness matrix. Stiffness matrix is 3 by 3. Okay. So if stiffness matrix is 3 by 3, now derive the stiffness matrix. Now you've actually find out what the stiffness matrix is. So stiffness matrix will, what is the thing? K11, K12, K13, K21, K22, K23, K31, K32, K33. These are the elements of stiffness matrix. What does K11 means? What does K11 means? So K11 means the force in the direction of first degree of freedom by applying a unit load, uh, by applying a unit displacement in the direction of first degree of freedom is K11. What about K12? The force uh, uh, the force in the direction of first degree of freedom when you apply unit load in the direction of second degree of freedom. Fine. So let us start finding out what is K11. So first, for that we need to label what are my degree of freedom 1, 2, and 3. We have this. Okay. Now what I'm trying to do is I'll try to take this. We I'm just trying to draw the singular. Okay. I'll take drift, or not the drift, sway. The sway has first degree of freedom. Okay. And the rotation here is second degree of freedom. Okay. And the rotation here I'll take it as third degree of freedom. Fine. So once you have that, so we can this is theta 2, and this is, I'll call it as delta 1. Okay. Now apply a unit displacement in the first degree of freedom and restrict or restrain the other degrees of freedom. So first column. Okay. What is my first column? The effective, or that is going to be I will apply, okay, in the degree of freedom No, no, sorry. Fine. So I'll be applying unit displacement delta is equal to 1, and what I'll be doing, I'll be restraining all the other degrees of freedom. So even this is restrained. If I do that, what am I going to do? So what I'll be getting? So this is going to be 6 EI delta is 1. So 6 EI delta 6 EI by L square, and this is 6 EI by L square. Okay. Then what about this? 6 EI by L square. So you need to be careful because in this lens are not the same. Anyways, this is H and this is H, so that is fine. This is going to be 6 EI by L square. Okay, but this is okay. It's going to be like this, right? This is 6 EI by L square, and this is 6 EI by L square. So what is going to happen here? I'll just draw it again. Okay, so this is 6 EI by H square, 6 EI by H square. This is 6 EI by H by 2 square. Then that is going to be L by H by 2, na? So H by 2 is 2 square. 2 square is 4. 6 4 is 24, na? So 24 by H square. This is 24 EI by H square. Okay, fine. Now okay, now we have applied unit displacement in 1 degree in the direction of the degree of freedom 1, and you need to find what one in you need to find moment in the second degree of freedom and moment in the direction of third degree of freedom. So that is quite simple. So let me, it's better I'll label it as A, B, C, D. Okay, so moment at C, right? So moment at C is how much? That is 6 EI by H square. 6 EI by H square. Fine. So moment at B is 24 EI by H square. 24 EI by H square. Fine. Now what is K11? K11 is the force in the direction of degree of freedom 1 when you apply a unit displacement in the degree in the degree of in the direction of degree of freedom 1. So this is 6 EI and this is 6 EI. And what about this? See, this is 6 EI. 6 EI plus 6 EI, you have 12 EI and 12 EI. So this should be this should be 12 EI by H square by H. That is H cube. Okay. And also you have something here coming here. So this is actually rotating everything in anti-clockwise direction. You should have a force that has to rotate in clockwise direction to negate it. So this will be 48 EI by H square by H by 2 again, right? So that is going to be 48 times 2 by H cube. Then what about the force here? Because that is what we actually want. So the force there is force at C, horizontal force, is 12 plus 48 times 2 is 96. 96 EI by H cube. That will be 108 EI by H cube. Okay. So this is nothing but K11. This is nothing but K21. This is sorry. This is K21. This is K31, and this is K11. Fine. Now let us find out what is the second row. Okay, second row. Second row K11, K2. Sorry, it's second column. Sorry, K12. So I need to apply a unit load at 2. If I'm going to apply a unit load at 2, how is that going to be? Okay, yeah, this is my okay. This is my actual thing. Everything is fixed initially, and now what I'm trying to do is I'm trying to apply a unit load at C. Okay, unit load at C. So that unit load is going to be anti-clockwise movement, because that is what we have assumed, if you remember. So let me rotate it by anti-clockwise, and this is going to be something like this, and this is going to be something like this. Okay, so this is theta 2 equal to 1. So this will generate a moment of how much? 4 EI by H. Okay, and this is 4 EI by H, and this is 2 EI by H. All right, and because of this you'll have a what? You have a carryover, right? It's 2. If it is 4 EI, it is 2 EI by H. Do we have any moments coming here? No, because it's a fixed. Like all the moments have been taken by the joint B itself. Okay. So now moment at C is 4 EI by H plus 4 EI by H. That is 8 by H. Now moment at B is 2 EI by H. Now force at C. Now that again, that is a challenge. So what is the force at C? Force at C is, so this is actually having the CD is having anti-clockwise rotation. So you should have a force which actually makes the body move in a clockwise rotation, so that we'll have a negative effect. So that is in this direction. Okay. So in this here it is something like this. So this is 6 EI by H square, and this is 6 EI by H square. So that is going to be 6 EI by H square. Similarly, even the third one. What is the third one? Third one is, what is the third one? Third one is you will be applying a unit load. You'll be applying a unit load at displacement at the degree of freedom 3. Huh? And then you'll find out what are the forces being in the other degrees of freedom. So you will again first initially assume all the members are fixed, and then you apply an anti-clockwise rotation. Okay, so this is theta equal to 1. Obviously theta should be equal to 1, because why the theta should be here 1? Because the rigidity has to be maintained, right? Is that the reason? No, that is not the reason. Because see, if you are actually rotating this support, the other side of the support is also rotating, right? I mean, the other side of the member is also rotating along with it. So that it's not about the rigidity here. because you are trying to rotate the support. You are trying to rotate the joint itself. So when you do that, you will generate 4 EI by H force here, and you'll generate 4 EI by this H. This H is H by 2 here. So this is H by 2. Okay, and because of this, you will get a 2 H carry over here, and because of this, you'll get 2 EI by H, and directly writing it as 4 EI by H directly. And do I get any force at D? I mean, moment at D? No, because it's already taken by C. There is nothing to transfer there, because the C itself is a carryover moment from the support B or the joint B. So moment at C is 2 EI by H anti-clockwise. Okay, moment at what? At B is 4 plus 8, 12 EI by H. Horizontal force at C is 6 we have, and you have 2 EI by H is H square, and you have 12 plus 4, 16. 16 by is it not 32? 16 by no, you have 8 plus 4. You have 8 plus 4, that is 8 plus 4, that is 12. 12 by H by 2, because the length is H by 2, that is 24. 24 EI by H square. Okay. Now we have obtained 3 columns. Okay, what are our 3 columns? Those are 3 columns. So stiffness matrix will be 108 EI by H cube, 6 EI by H square, 24 EI by H square, 6 EI by H square, 8 EI by H, 2 EI by H. This you can just find out here. 8 EI by H, 2 EI by H, 6 EI by H. Okay, H square. 24 EI by H square, 2 EI by H, 12 EI by H. So this is the stiffness matrix. Okay. So yeah, once you know the stiffness matrix, you can easily find out what are your forces at those degrees of freedoms. So in the question, what was asked? So let us say in the question it is you are applying a force P, right? In this, here you are applying a force P. So that is actually in which degree of freedom? One. This is one, 1, 2, 2, 3. So P is in actually the degree of freedom is 1. P0, you already found out what is K. D1, D2, D3. You can simply find out, right? What are your D1 is actually the horizontal sway. D2 is rotation at the joint 1, A, B, C, D. D1 is horizontal sway. D2 is rotation at joint C. D3 is rotation at joint B. Okay, that is quite direct. Like once you find out what is stiffness matrix, you can directly find out what are the rotations and I what are the rotations and what are the horizontals way. Fine. So that is what that is what I want to cover for this session. Um, once once we are again once we just a quick recap. We try to formulate the stiffness matrix for a beam for a beam member. We try to formulate the different and we try to compute different elements in the stiffness matrix. So the size of the stiffness matrix is actually the degree of freedom, so the kinematic indeterminacy. Uh, so we try to compute for the beam member, and then what is the second step? Once we found out the stiffness matrix, we can find out the unknown forces or the unknown displacements. Okay, by the compatibility condition. What is the compatibility condition? Compatibility condition is nothing but the force is the matrix multiplication of the stiffness matrix uh, with the displacements. Okay, so that is what I want to cover for this video session. And most probably uh, most probably we may have one more session. Maybe it's a summary session or it's a recap session before your final exam. So yeah, we will discuss some topics during that, and we'll have a quick recap and quick summary of all the concepts which we have learned on the structural analysis. Again, we will start with determinate structures, truss analysis, frame analysis, and also the beam analysis, and then we'll go to the ILDs, the influence line diagrams, and then to the indeterminate structure analysis. So indeterminate structure we started with the energy methods and then the compatibility conditions. So we have used flexibility methods there, and after that we have derived the slope deflection equations and then the moment distribution method, and then introduction to the stiffness matrix. Okay, fine. Then now I'll sign out, and thank you for your patience, and thank you for listening.